starting. Record. Right. Okay. Now we go. Right. So, hello everyone. Welcome to session 21 of BGA24. This session is on the VGP-Galaxy assembly pipeline with Delphine Lariviere. Please take it away.
Thank you. So I'm going to share my screen. Can you all see the slides?
We can indeed.
So thank you for joining today. So I'm going to present today the how to assemble genome in Galaxy with a VGP pipeline. And we're going to start with a real quick introduction to what is Galaxy, how assembly works, and how we implemented this VGP workflow in Galaxy. And then we're going to go through a hands-on to show you how to use them, where to find all the data and the workflows. So Galaxy is a platform, it's an interface to run tools. It started with genomic, but now it extended to a wide range of different types of analysis. And the goal of this platform is to allow for accessible, reproducible, and collaborative data, whether you want to run one analysis, many analyses, and if you want to share your work and share your data with your collaborator or with the world. So Galaxy is running tool interactively. There's thousands of tools in the toolshed that can be installed in any Galaxy you can find. We have created reference data. We can support workflow functionality, running thousands of samples at the time. And we also run Jupyter, RStudio, and interactive tools. So you can streamline, have your workflow for production, and then you can fine-tune your analysis by exporting your data in Jupyter, and all of that without leaving the website, the platform. There's a huge community supporting this platform, whether it's for developing tool, developing new functionality, and also developing training material, among them the one that we're going to use today for the hands-on. So there's a lot of mini Galaxy. There's local instances for labs. There's national instances like Belgium or French instances, but there's the big main three instances, which is usegalaxy.org.eu and .org.au for Australia. So the one we're going to use today is galaxy.org. I'll send you all the links to follow the hands-on in the chat. And this big project, we would be nothing if we didn't have this big community of scientists and developers and people using these tools. And we had the big collaboration for a couple of years now with the Vertebrate Genome Project, which aimed to sequence. The goal of the project is to have up to 70,000 species of vertebrates. Phase 1 just finished with hundreds of species that represent different order of vertebrates. And we collaborated with them for a couple of years now, as I said, and we've assembled more than 150 genome in Galaxy from the VGP, just from the Vertebrate Genome Lab. It's been used with other labs, but I don't have this number, but I know other people use it. And so I'm going to talk a little bit what data we use for this genome assembly and what process this workflow implements. So the main data that we are using is PacBio hi-fi data. So it's called circular consensus read. So this is technology that allows to read several times a single piece of DNA. So this double-stranded DNA is circularized and it's read several times. So every error is compensated by reread. So it allows to have long read that are very high quality. It used to be expensive, but it's very manageable now. So it's accessible to a lot of lab, which is also why we want to make this workflow accessible to everyone, because this is technology that is become accessible even for low budget projects. And Galaxy, with all the resources that we're providing for free, allow us to give this project high quality analysis of the sequencing. The other main technology that we're using is ARIMA IC. So ARIMA IC is based on the principle that in the nucleus, chromosomes are packed together. One chromosome is packed together with itself. And what IC does, it is sequence it's paired read, and it sequences two strands of DNA that are physically closed in the nucleus, which means that across the genome, the more high-seed reads you're going to have, the more likely two sequences are to be closed in 3D, but also across one chromosome. So what you get is this heat map data, where you can see that across one strand of DNA, you have very strong contact between a high-seed read when you are close, and then it gets lighter and lighter the further across the sequence you get. And this gives us information about large-scale organization of the sequence. And so I'm going to talk, we're using this data at several steps of the assembly, and I'm going to talk a little bit in detail later. Another type of high distance data that we can use, I'm not going to show you the workflow today because we're going to use simpler version of the process, but we also can use binary-optical mapping data. So binary-optical mapping is highlighting probes across the sequence of the DNA, whose sequence we know. And so we kind of see these probes that we know are separated by this number of reads. So it gives us large scale and allows us to organize contigs comparatively to each other. So this is also available in the data. And so once we have all these reads, all this data, assembling a genome has three main steps. Once you have your DNA sequences, your reads, you're going to construct assembly graph. You're going to simplify this graph. So these two steps are called continging. And then we are going to detangle this graph with this high distance information, which is provided by Hi-C and by BioNanoData. So this last step is called scaffolding. So I'm going to talk a little bit more in detail about continging, because one of the big important information that you're going to encounter when you're continging is this KMR word. So you're going to divide your reads into shorter sequences of set length. So, for example, you have your reads, and you're going to divide it in KMRs of 12, and they're going to be separated by one base every time. And so you're going to build these graphs that are overlapping one KMR by the other. And when you have a variation, SNP or heterozygosity in your graph, you're going to find yourself with this bubble, because suddenly you have two paths, two different KMR, and this is going to be the size of the KMR, because it's going to be one base separated every time. And so you have this graph, this ideal graph, when you have one sequence and a bubble when you have heterozygosity. In practice, it's a bit more complex because you have repeats, you have error of sequencing, but essentially what we want to look at is this kind of graph. And so this kind of bubble, they represent the diploid genome. What we're interested in is having the two haplotypes, which means we want the strand of DNA who comes from the mother, the strand of DNA who comes from the father. And so to separate these two sequence of DNA, it's called phasing. So when you don't have any information, you use simple phasing, which means each bubble is resolved randomly. If you have two bubbles next to each other, one strand are going to be in one haplotype, the other strand on the other haplotype, and you're not going to have additional information for that. The ideal case is if you have data from your parents, and you can see, okay, this came, so this side of the bubble, we find it in the mother, the other one in the father, and so you can kind of have all these bubbles resolved on the side they belong to. But it's rare that we have this information for chiro data, especially when you have sample in the wild, you have your individual, you have no idea who the parents are. And it's been shown that using this IC, this conformation 3D information is doing actually a great job at resolving this bubble, because you have this large information, which means you can have reads that cover two bubbles that are distant from each other, but you know they belong to the same chromosome. And so you can see, okay, these two sides belong together. So we don't know which one belongs to the father, which one to the father, but we know they belong to the same parent. And so that's what we're going to use today. Is we're using this high-C data in addition to the high-Fi data to get these two haplotypes phased. Then you have the scaffolding step where we're using high-C data, and this allows us to organize the contigs together. And so these are, as I said, large-scale information. So you don't know how the scaffold attached to one to the other. So that's what's going to create gap in your assembly. So you're going to have two contigs attached together with a sequence we don't know how long, and that's going to be completed by gaps, which are sequences of ends in the genome. So all of these processes that are presented, we implemented them in Galaxy for 10 workflows, sorry. So depending on the data that you have, you're going to use different workflow and different pathway. So you have a first step, which is schema profiling. I'm going to discuss a little bit later exactly what that means. You have the contigging step. You have optional purging step. Again, I'll describe a bit what it means, the scaffolding step, and then you can decontaminate your assembly and assemble the mitogenome with the same data. So today we're going to see what we used. This is the main analysis that we use for most of the genome in the VGP project, which is we have high-Fi data, we have IC data. So we're using contigging with IC and scaffolding with IC. So I'm going to share the link for the hands-on. So the first link is you need to be identified on galaxy.org. So if you don't have an account, please create one. And then when you click on this link, you're going to get to a preferential queue, so your job runs faster for today. I'm also going to link the training material when you're going to find more detail if you want to follow along. And we're going to go to Galaxy and the training material. So this training material has been developed. You have two versions. Today, I'm going to do the shorter version when we're using on the workflow. If you want to go into more detail, we have the step-by-step where we describe why we're using every tool and what parameters we're using every time. So I'm going to do a shorter version. We're going to run everything, but we're not necessarily going to wait for everything to run because it might be a bit long. But I've pre-run a lot of things so we can look at them together. So if you're going to Galaxy, you can create a new history. And I'm going to show you that you can upload data from different. So sorry, I'm going to a bit fast here. So on the right here, you have your history, which is where all your data is going to store along the analysis. You have the activity bar on the left, and you have your main window here where most of the interaction are going to happen. So if you want to upload data into Galaxy, you can click on the upload on the activity bar on the left, and you have different options. You can choose local files from your computer. You can choose remote file. Here, for example, we can have access to Genome Arc, which is the VGP repository. And you have access to all the raw data and all the assembly that have been produced by the VGP project. So you go to species and you have all the species and all the data in there. And finally, the third way is you can paste URL. which we would do normally if we had time for that, but I pre-uploaded the data for you so we don't have for it to upload. And you can find that by going into histories on your activity bar. Please let me know if I'm going too fast, interrupt me for any question. So once you're in the history, you have all the history that you have worked, but where we want to go is to public history on the top here. And if you search for BGP, you're going to find this BGA 2024 starting data. So if you click on this and view, you will have copy this history. This one belongs to me, so I don't have the same button, but you should have copy this history. So once you've done that, you can come back to the main window, clicking on the little house. And you should have this data here. So the first three data sets, we're going to work with artificially generated data from a yeast. So we have 3 PacBio data sets. This one are faster, but from your sequencing runs, you should have FASTQ files. And we have 2 sets of high-C data, which correspond to forward read and reverse read. So these names are not really talking to us. So the first thing we're going to see is we're going to rename our files so we can find them more easily. So to rename a file, you're going to go in the history on the right and click on the little pencil button. And we're going to call that high-C forward read. And we're going to save and do the same thing with the reverse read. Either pencil and you see it rename the file in the history. Now, the second step that we're going to do to prepare our data in a history is when we're going to run our tool and our workflow, we don't want to run it 3 times in all of these things. So in Galaxy, we have what we call collection, which are folder containing data sets, and they're going to be considered as a single object. Depending on the tools, sometimes it's going to, if you give a connection to it, it's going to consider that, oh, all these data sets belong to one analysis and we're going to merge them together. And sometimes it's going to consider that as different analysis and run 3 times the tool and give you a collection with all the output of the 3 ones. In that case, this workflow that we're using, they consider PacBio as one single analysis. So if you have several PacBio organisms, you want to have one collection per organism and don't put all your data in one collection. So to create a collection, you're going to click on the little checkbox marks here to display the checkbox for each data set, and we're going to select our 3 hi-fi data. Once you've done that, you click on the 3 out of 5 selected, and you do build a dataset list. And we're going to call it hi-fi data. And you see it created a collection, so you can hide the check mark box now. You can click on the collection and you see that it expands and you have your 3 data sets inside it. So the first workflow that we're going to run is called K-MER profiling. So if you want to find the workflow, you can scroll down and you can click on Launch Genome Profile Analysis. So mine by default is .org. If you don't have .org by default, you can select it in the preferred Galaxy server. And you see that we're going to arrive in this form that we're going to complete to run this workflow. So this one is it's a simple inputs. We're going to input the hi-fi data collection that we just created. And we're going to select the camera length that we want to use. So in that case, we're going to select 31. And we're going to provide the priority of our species. In our case, it's priority of 2. So once you run all of that, you're going to click on Run Workflow. And you're going to arrive to this view when you see what your workflow looks like. So you have your inputs there. They're linked to each box is a tool. And it distributes the inputs. And you can see, if you stay at this view, you're going to see them turn green one by one. And that's going to show that your jobs are done running. You're going to have the same phenomenon. You see that in the history on the right is being populated by all the output of the workflow. So it's going to be gray while it's waiting to run. It's going to be yellow while it's running, and then green when it's done running. So you can see that we have several output here. We have Mary database, which is a count of all the cameras that are found in the reads, and the genome scope profile. So while it's running, I want to talk a little more about what is camera profiling. So camera counting, we're going to divide our reads, as I said earlier, into camera of a definite length. So we selected 31 in our case. And it's going to count how many times this read, this camera are found in the read. So there's an important distinction here to make. When you select your camera size in your assembly, the goal is to select a length that is long enough that you're going to only find them once in your genome. Because the goal is to have this graph, and if you find your camera several times in two distinct places, the graph is not going to know how to attach this camera together. But this camera, since you have X read covering your genome, you're going to find them X time this camera compared to the genome. So you're counting how many times you found them in the reads in this step. And so you're going to get this kind of profile. You're counting how many of single camera you found in the reads. And you're going to find that here, for example, we selected a haploid sequence of 121 gigabase pair of reads from a human genome, which is 3 gigabase. And you see that indeed the coverage is about 40x. So every camera of the genome is found 40 times in the reads, which makes sense because you have about 40x coverage of the reads. You also find, so you have the distribution, and you also find cameras that are present in very low quantity, and these are cameras that have sequencing error because you don't find them in all the reads, so the coverage is way lower than the expected coverage. So this was for a homozygous region, for, sorry, a haploid genome. And what it looks like when you have a haploid genome is you have these two peaks, because when you have a camera that is present in 2 copies of the genome, you're going to find them twice as much in the read because you have the coverage from the paternal and coverage from the maternal reads. And it's going to be double the coverage of the heterozygous region. And so the 2 peaks are going to be different height depending on the heterozygosity of the genome. So that's why we do this camera count, because it gives us precious information on the quality of the reads, whether you have a lot of error camera, whether you can count, you can assess the heterozygosity depending on the height of the 2 peaks. And so this is what GenomeScope does. It creates this camera count, and it creates this model that fits this histogram, and it uses this model to evaluate the length of the genome, the heterozygosity, and the coverage. So this is what we run in Galaxy. So you have the Murray database, which is the count, and you have this GenomeScope data that are the estimation of the models. So I pre-run it. What it looks like when it's done running, you can see that we have these two peaks and we have heterozygosity at about 0.58. So one thing to be mindful of when you look at this histogram is you want to check if the black line, which is the model, fits your histogram well. If it's not, you might have incorrect estimation. One way to remedy to that is trying to change the camera size to have more defined peaks and tweak this kind of parameters. So these are the main inputs of this workflow. And another important thing is all these data, you have them in text output, not just in image output. So we're going to use this text output to generate estimated genome size, what is the average coverage, and this parameter we're going to use in later workflow to as parameters for the containing. Everyone good so far? I'm not going too fast? Perfect. So the next step, now that we have this camera count, is we're going to go through the containing step. So this containing step, we're using hi-fiism. So hi-fiism is building these graph bubbles and then separating them into two haplotypes. So if you use hi-fiism only on hi-fi data, as I said earlier, you're going to get two types of assembly. You're going to get the primary assembly, which is all the homozygous region plus one side of the bubble of the heterozygous region. And the alternate assembly is going to be only the other side of the bubbles. So if you have primary and alternate, all the scaffolding step, etc., is going to be all done on the primary. But in our case, we're going to use hi-fiism and hi-C. So after it builds the assembly graph, it's going to include the hi-C read, map the hi-C read to the assembly graph, and it's going to divide this bubble together and gives us a phase assembly. And in this case, you're going to have haplotype 1 and haplotype 2, and both are complete assemblies. So in a typical VGP project, we're going to run the scaffolding on both haplotypes, and then we're going to curate both haplotypes separately. And so you're going to end up with two references, which are two haplotypes. So in order to do that, so we're going to go back to the link. We're going to go back to the training material. And we're going to go to the containing step. So as before, you're going to launch, click on the link, select galaxy.org. And this one, there's a bit more parameters. So the first part is, as before, we're going to use the hi-fi pack by reads. So if your history is a bit large, you can start typing the name and we're going to get your hi-fi data. Or I'm going to go back to the one we just ran. Okay, so hi-fi data, forward read, you're going to select forward reads, reverse, reverse. And we're going to use the model summary. And this is going to give us information that allows us to feed to the next workflow, the heterozygosity, the coverage, and the genome size. We're going to provide memory database. And we're going to select the lineage, which is Ascomycota. I'm not sure how to pronounce that. Okay, and genome scope model parameters, there's only one choice. So A couple parameters I can talk about is Bloom filter. If you find that you have a large genome and you have memory errors, you can try to change the Bloom filter. And this parameter here, we're not touching it because we trust our genome scope profile. If you find that the genome scope profile doesn't really fit and you don't agree with what your average coverage is, or if you find that down the line your assembly looks weird, you can manually enter the read coverage for KMers for heterozygous region, so the first peak. But in that case, we're trusting genome scope, so we're going to trust that it's going to use the model parameter well. So you can run workflow. And we're going to see this one is a bit more massive than the previous one. So there's a lot of data manipulation, organizing the column, parsing the file. But we're going to take a look at a couple outputs that are important. I'm going to give you information on what your containing step quality is. So while it's running, I'm going to go to the one I ran before. And the first thing that we're going to look at Brusco. Where is Brusco? So we're going to look at Brusco summary image. If you're like me and the image are a bit overblown, you can open image in a new tab and it's more readable. So Brusco is a tool that gives you information about genome completeness and genome duplication. So what Brusco does is it has this set of genes. So that's why we provided a lineage, in our case, as Komikota. But for most of the VGP genome that we're running, we're using vertebrates. And it's looking for a set of genes that are known to be present in all the family in only one copy. So a perfect genome, if you have the exact true genome, for the vertebrate, you would have all complete and single copy, assuming that you have a very stringent selection of taxonomy. And so if you have duplication, you're going to have a high number of dark blue genes, which are present but in multiple copy. And you have fragmented, which means that we find part of the gene that are expected to be found, but there may be across different contigs, or it's been part of the gene has been missed. And red you have missing. So you're never going to get, in actuality, a full light blue, because you're using vertebrate, but some species might have duplicated genes that are not present in all the vertebrate, or some genes that disappear that have been transformed. And so if you have 90%, 85, 90% of blue, it's a good containing step. But if you have a lot of dark blue, you might want to think maybe I have duplication in my genome that are not, in my assembly, that are not actual duplication in reality. Another evidence that you can look at for these duplications is mercury. So mercury gives you different outputs, but the one we want to look at is the plot. So it's a collection, so you're going to click on it, and you're going to have all this data here. So you can look at, so you have 0, 1, which is for haplotype 1, 0, 2, which is for haplotype 2, and the one that show both assembly. So we're going to look at the first one, and you're going to see that you find similar plots than we had when we were looking at the KMer profile. You have the KMer multiplicity in the reads and the counts instead of the frequency. But the extra layer of information we have is the color, and that's the number of times the KMer is found in the assembly. So you can see here, we have one peak for, so we're looking here at only one of the haplotype. So in gray, you have chimeras that are found in the reads, but reads only, not in the assembly. And you see that the peak correspond to heterozygous region, which makes sense because we're looking at only one assembly. So this read, this camera belongs to the read that map to the other haplotype. If you find that you have a peak of read-only that is corresponding to the peak of homozygous, you think, okay, maybe I have a missing region in my genome that I didn't assemble properly from my reads. And the only thing we want to look at is you want your camera to be present only one copy in the genome, so red is fine. If you have large peak at 2 or more, you think, okay, I probably have region in my genome that are duplicated. So a little peak happens, you might have repeats and duplicated natural duplication. But if you have a peak that is significant, you might want to look at purging your assembly. And what it looks like is when you need to purge your assembly, it's going to look something like that. So you're going to have your peak. So this one is for 2 assemblies. So the read-only is, no, sorry, that's for haplotype 1. So that's similar to what we just looked at, but this one doesn't have, is colored differently. So you have your peak of reads that belong to the other assembly. You have your 2 peaks of chimeras that are in one copy only in the genome, but in the reads you have your 2 peaks. And then you see that the one that we didn't have in the image we just showed, like the blue plot, we have a huge peak of chimeras that are present in 2 copies in the assembly. So that is caused because you have these contigs that are assembled, but they overlap. And so when you look at the copy number, instead of having one camera, you have this region where you have these cameras that are doubled. So what the purging step does is it cuts this contig, so there are no artificial overlap. And after purging, you get this clean graph that are where the blue plot disappeared. So we're not going to run it because we see that in our assembly today, we don't have this blue plot, but you have in the slide the link to DocStore, and if you find that your genome has duplication, sorry, if you find that your genome has duplication, you can run it on your data. So you have all these workflows that are available, and their number corresponds to the one in this image. So 1, 2, 3, to 10, up to 9, sorry. So back to our Galaxy. You also have, what do you have? Assembly stats that are assembly statistics for HAP1 and HAP2. So they're generated by GFA stats. And these assembly statistics give you information about how many contigs do you have, how many scaffolds do you have, what is the length of your assembly, so you can compare that to the estimated genome length. And you have the number of gaps, so you shouldn't have any of these steps because the gaps appear, as I said before, when you scaffold, which means when you order contig in relation to each other. So this allows you to compare both the quality between haplotype 1 and haplotype 2, but also along the way, how much your assembly improve at each step, after purging, after scaffolding, etc. Okay, so we can come back to what's running. So the final step is, so we have this config. You may or may not need to purge them, but you're going to get config after purging. And the final step is high-C scaffolding. So high-C scaffolding is, sorry, I'm going back here. There you go. High-C scaffolding is workflow 8. So again, we're going to click on opening a new tab, and we're going to run on galaxy.org. Okay, so this one, we're going to use GFA file. So you're going to run this. We run this at least in the VGP project twice, once on upper type 1 and once on upper type 2. And again, we're going to select the same lineage and previously. High-C forward reads, High-C reverse reads. And the restriction enzyme is going to depend on the technology you use to generate your High-C data. So for this tutorial, since we're using artificial reads, we're using enzyme-free prep. Estimated genome size, as should have been generated by the previous workflow. So you can type estimated genome size, and that's all we're going to change. And we're going to run the workflow. So once it's running, you'll be able to look at so once again, you're going to have your blue score information, server image. And you can verify that you didn't lose too much gene when you scaffold, because sometimes you might have purging step or some gap that appear that make you lose some genes. So you shouldn't move too much from the BSCO to the from the context to the scaffold. You have some plots that gives you information about the cumulated size of your scaffolds, the NX plots. So NX is X is a percentage. So for example, N50 is the size of the longest I have a slide for that. It's so 50% of the genome is contained as large as N50, which means you're going to have your genome order from the largest to the longest, and 50% of the genome, this is going to be the size of your N50. So a higher N50 means you have bigger genome and a less fragmented assembly. So you can look at the NX, N90, N80, etc. And that gives you information about how fragmented your genome are, and if you have a lot of big scaffold and a lot of small scaffold, it gives you information about what your assembly looks like. You also have the same stats as previously, the number of scaffold, this time how many gaps you have in your scaffold, and different information about your assembly. But one important thing that we're going to look at that we didn't have in the previous step is the High-C map. So High-C map, as I described earlier, is you should have, it's better with the grid, you should have this scaffold contact within the scaffolds and not across the scaffolds. So this one is very clean, but if you look at the hands-on, you have an example for the zebrafinch. And first you see that after scaffolding with IC, you have a lot less scaffolds. And you see that you have this map, this heat map that are within scaffolds and not across scaffold, except for this. Can I make it bigger? Yes. Except for this scaffold, and you see, okay, this is an indication that when you go through manual curation, you might want to merge the scaffold because they probably belong to the same chromosome. So this gives you information about yeah, so it's giving information in post-assembly, in manual curation, whether you should merge. Sometimes you're going to have this X pattern. Here, you would have this scaffold here where you have a part where it's not actually in contact, and that may be a sign that this has been scaffolded by mistake, and they might actually belong to two different chromosomes. You also have this kind of microchromosome that are so small that they are so close together in the cell that kind of they have contact between each other. But so you have a lot of information from this high C map. So that is mostly what we can see in this yeast assembly. If you want to look at what the real case data is, you can go back to history, public history. VGP again. And look at the zebrafinch. So you see we have the same output that we had for the yeast, and you can take a look at the different plots. So here we have a different kind of heterozygosity. It's higher, so like the peaks are different than what we had for the yeast. When you look at the Busco image, you can see that we have a genome that is quite complete and without, it doesn't look like we have duplication that we should be worried about. We can look at the mercury plots. Again, same thing. We don't see any peak in the blue or above plots. When we look at the haplotype 2, it's the same thing. We don't seem to have to worry about duplication when we look at mercury as well. And we're going to look at the pretext full map. So you can see here that's before the high C scaffolding, and these are contigs. So it makes sense that it's all over the place. It's small. It's not resolved clearly. And when we look at the scaffold after that, that is way cleaner. And as I was saying before, you have this scaffold that you probably want to join in post-assembly curation. And you have this square of microchromosome that seems to be close together in the genome. So these pretext snapshots are generated, but most of the people, when they work on curation, they're going to use the pretext map. So that's one thing I didn't mention. When you run all this workflow, it's creating a lot of output, but most of them are hidden because there's a lot of step, which is cut a colon, make operation on file, that you don't really need to see every single intermediate step. But if you need, for any reason, to look at intermediate step, you can click on the little include hidden, and then you see that you have all this intermediate file. And it's a bit more confusing, but you can find it. And so this pretext full map that are somewhere. So this pretext format, you can download them and visualize them on your computer and rearrange your scaffold together, highlight some data, overlap information like gaps, telomere, coverage, and all of this is going to help you find more information on improving manually your assembly. And that brings me to this slide, which is, okay, now we have all these workflows are used in production, and we can run several assembly a week. It can go very fast. As you see, you just fill up free form, run it, and wait for it, come back a couple of days later, it ran. But the bottleneck to create this high quality reference data is manual curation, because it takes a lot of time. You have to manipulate your scaffold, look at your evidence, and we are trying to make that process as streamlined as possible. And so for that, we have a pre-curation workflow that is coming soon, and it computes how many, it identifies the repeats in the genome, the gaps, the telomeres. It shows the coverage. Coverage is important because if you have variation coverage, it might be, if you have low coverage somewhere, you might be less trustful of this part of the assembly. If you see that suddenly you have double the coverage, you may have a duplication that should be there but has been merged into one region in the assembly. So it gives you an indication on how much trust you can have in this region of the assembly. It also produces dot plots. So dot plots are useful. You can compare either one haplotype against the other. So dot plot it's mapping two genome against the other, and it tells you, okay, each dot is a region that is found in both sequence and where they are in the scaffold. So what you expect to find if you have two sequences that are identical, you have this nice diagonal where scaffold one is the same as scaffold one on the other assembly. And it gives you information on how to organize your scaffold, which scaffold in one assembly correspond to the scaffold on the other assembly. So like both the scaffold are chromosome 1 and they map together. It looks fine. It also gives you information on, well, that's weird because half of this scaffold I find in one scaffold and the other, and I might have a misassembly because the dot plot don't align. It gives you a lot of different information. And it also can show you, okay, this scaffold is in one assembly, not at all in the other. That might be a sexual chromosome. So all this information we are computing them in this workflow. All of this is available in GBRO, so you can visualize it, and the goal is to accelerate this manual creation. So we are working on publishing these workflows. And another workflow that we have available in the VGP is the assembly decontamination. So assembly decontamination, it's a different workflow, and it's a different tutorial, sorry, and I'm going to share the link. So we're going to take a look. This one is a quick workflow, but it's important because it's going to depend a lot, your contamination of your assembly, on the quality of your sample. if you have an individual that you have been able to collect in good condition, you shouldn't have any contamination. But sometimes you have tissues that are degraded or are mixed up with each other. You have contamination from the environment or from the collection. And also, you're going to have in your assembly sequence that are going to correspond to mitochondrial sequence. So when you publish a workflow, when you publish a genome assembly, you want to separate the nuclear genome from the mitochondrial genome. You want to identify what is from the mitochondrial genome. So you have workflow that's going to build the mitochondrial genome from the PacBio data that you're going to run in parallel of your assembly. But you also want to remove them from the general assembly because they're going to be mixed up together. So what we're going to do is we're going to go to the tutorial and we're going to upload this assembly that we just finished running. So we're going to go back to Galaxy, we're going to create a new history, and we're going to go to upload data, past stage data, and we're going to paste the URL of our assembly. And we're going to click start, and we see that it's going to appear in our history. So we're going to rename our history because we want to, believe me, when I started working on Galaxy, I had 20 unnamed history, and I learned very fast that I should name all my history. It gets very confusing very fast. So we're going to call that, as you want, tutorial decontamination, for example. And the first thing we're going to do is, see, you don't have to, but it's good practice, is we're going to mask our assembly. So masking is, it's going to identify any region of the genome that is not very informative. So everything that is repeat, tell me repeat, or short repeat, or it's something that won't give you information about which is going to be not going to be very distinctive. You can leave them, but it's going to be more computively intensive for the tool to run on a masked genome because it's going to look at all the genome. If you mask them, it's going to tell the tool, you can ignore this, it's not giving you any important information. And this is for classification. You want to keep only the sequences that are maybe peculiar to a species. So you don't have to, but it's going to accelerate and improve the memory usage of the tool. And in order to do that, we're going to use the tool Dust Masker. So there's two types of masking. Sorry, you're going to tool. There's two types of masking. The first type is soft masking. So it's going to just, all these repeats that are not very informative is going to put them in lowercase. Some tool recognize that as I should ignore this part, it's not going to give me any important information. But if you're not sure that the tool is going to recognize that information, you should hard mask it, which is all the sequence that are repetitive is going to put N inside, the letter N instead of the base. So we're going to use the tool called Dust Masker. So you can click on the tool on the activity bar and search Dust Masker. So you want to use the FASTA file because, yes, you want to mask the sequence from your file. Are we changing anything else? That's level 40. So when you look at your assembly, you see that you have this region that seems to be very repetitive, CCC, TAA, CCC, TAA, etc., etc. So what we expect is this region is going to be masked in the masked file. Sorry. I think I made a mistake. See, format mask info, that's not what we want. We actually want the FASTA file. So if you want to rerun the tool, if like me, you forgot to change a parameter, you can unfold, click on the data sets on the history, click on the little turning arrow, and it's going to autofill the formula with the form with what parameters you changed before. So the parameter we're going to change is output format. We want the FASTA file because we're going to use that as a base to classify our sequences. And we can cancel the job. You can click on cancel the job by clicking delete on the one where I made a mistake. Should have decontamination from the. Sorry, I didn't expect to go so fast, so I didn't plan for running this one in advance. But it should run pretty fast. Can't find another one. Okay, so while it's running, we're gonna run the hard masking. And so this one is a bit more tricky because we don't have a tool to go from soft masking to hard masking. So what we're gonna do is gonna use a regular expression to just replace any lowercase by ends in our sequence. So we're gonna do that by using the tool text transformation. We're going to run that on the masked, soft masked assembly. And we're going to use this set program. So I'm going to go a bit more in depth in that. So what it means, so this part means we're only applying this change to sequence that don't start with a arrow, which means we're ignoring the FASTA headers. Then what we're doing is mapping one-to-one. So this first character is going to be replaced by this first character, second character by second character, etc. So any lowercase base is going to be replaced by an n in the sequence. So we can run that. Little tip, if you want to test your regex, I think the regex 101 allows you to test your regex on, you can put your test string and test it because it's a pain to find the right regex for your tools. Okay, so now that we have, once we have these masked sequences, we're going to run two different paths. One path is going to identify contaminants, and one path is going to identify mitochondrial data. So to identify non-target contaminants, in this tutorial, we're using Kraken 2, but we're soon going to publish a new version of this using FCS-GX from NCBI. But for this Kraken 2 tutorial, we're going to use, so the tool Kraken 2. We're using single because it's actually an assembly, so it's not paired data. So we're using it on the hard masked assembly. We want to print the scientific name because we want to know what type of contaminant we have in our sequences. Confidence 0.3. We want to split the classified and classified output. I want to split them because what we're going to do is once we get two, we're going to get two FASTA. One FASTA is going to be the classified sequence and the unclassified sequence. So one important thing here that is to note is we're going to use database to identify the contaminant, which means everything that is unclassified belongs to our species. Because the database we're going to use contain viruses, bacteria, protozoa, and human data. Because human data is a common contaminant because that's why you need to wear gloves, because you tend to send your DNA and everything. And so we're going to use database called PlusPF. And so it's going to identify only contaminants. So once we get these two FASTA files, we're going to see, we're not going to use them as is because remember they are hard masks. So we are losing some information when we hard mask the data. So what we're going to do is instead of using this unclassified reads as our new assembly, we're going to get the name of the classified data and just remove them from for the original assembly. That's why we're going to do a little bit of text manipulation, but that's because we don't want to lose information from the hard masking. So while it's running, we're going to look at identifying mitochondrial DNA. And for the mitochondrial DNA, we're going to use BLAST-N. And we're using BLAST-N because we're looking at nucleotide sequence from our assembly, and we're using it against a database of nucleotide sequence, which are mitochondrial DNA. So we're using it on our hard mask assembly, and we're going to use locally installed BLAST database, and this is RefSec mitochondrion. So remove the HCS one, just select RefSec mitochondrion. We want to run BLAST-N. And we want a BLAST tabular. There you go. Tabular select which column. And the reason why we're changing the column is because we're going to use a tool called Parse BLAST, which is a script that has been developed by the VGP lab that is parsing this result and extracting mitochondrial sequence. So you won't have, as you have to do for Kraken, all this manipulation of extracting data from. It's going to do the work for you, but it means that you need to have the specific tabular output. So you have the list in the tutorial. We're going to select QSEC ID, SSEC ID. Length, QStart, QEnd, any value. So you can unselect the other ones. Extended colon, we're going to select QLen. And miscellaneous QCurve and QCurve HSP. Okay, and run the tools. And so this Parse BLAST, because you're going to see when it's done running, it's not really human readable. It's stable with statistics between sequences. It's a bit hard to parse by yourself. So that's why we're using Parse mitochondrial BLAST in the tool. And we're going to run it on the last end result. So we're going to wait a little bit for it to run. Is there any question that I can answer in the meantime? Um, let me think. Okay, so the next step, we're going to come back a little above, and we're going to extract information about our contaminants from Kraken. So we're going to do that by just passing the column, because the output of Kraken is going to give you a tabular file which has 5 columns. The first column is going to be C or U, saying it's either a classified sequence or unclassified sequence. And so we're going to filter on this sequence. We just want to extract the classified sequence because these are going to be our contaminants. We have the sequence ID, so which scaffold correspond to contaminant. The taxonomy ID, which is what has been what species it belongs to, identified by Kraken. So these are the 3 information that we want to extract. The other one that we don't care much for in this case is the length of the sequence, and it gives the 5th column gives information Kmer by Kmer what taxonomy they belong to. So it's a very detailed step Kmer by Kmer of the sequence, which we're not going to use in this case. So we're going to extract the first 3 columns from this tabular file, and we're going to do that by using the cut tool in Galaxy. So we're going to cut columns C1, C2, and C3. It's a tabular file. And we're going to do that on the classification of Kraken. And then we're going to filter these 3 columns and select only the classified sequence, and we're going to do that by using the filter tool. So we want column 1 to be equal to classified, and we want that on the cut, which is the file where we selected only the first 3 columns. So as you see, there's a lot of steps when you have to cut, filter, select. You don't want to do that every time. So one simple way of creating a workflow when you run, you're going to run your history, try different tools, try different parameters. And once you find what works, you can go into your history option and you can use extract workflow from the history. So this one is not done running. I'm going to use another example for that. What do I have? So for example, I'm going to extract the workflow, and you can select, okay, these are the output where I use the right parameters, and you can select or unselect which one you want. And you can create a workflow. And you see that it created the input and plugged everything in the right place. And then you can rename however you want, change whatever parameter you want. So if you want to run exactly the same analysis every time, you don't need to change anything. If you think that there's some parameters that you need to change from one species to the other, you're going to click on the tool and you're going to select this example here, which is, okay, this one is going to change every time I run it. So I want to ask the user what they want to set, for example. And this is a little arrow. And so that's where you can create your workflow easily and repeat your analysis without going through every step every time. I think that's it. The last step is extracting the name and using GFA stats to remove it. So to extract the name, we're going to use the cut again, except we're going to use only column 2 because that's where the name of the sequence are, and it's going to give us just a list of one scaffold name per line. And we're going to use that as an information to say to GFS stats, please remove these sequences from my assembly. So we're just going to use C2, and we're going to use that on the filter that we just ran. And we're going to concatenate the output from the two paths. So we had two paths. We had one that identify which are the contaminant, and one path which sequences belong to the mitochondria. And so we're going to concatenate these two data sets, and we're going to use concatenate, and we're going to use that on the cut that we just ran and the output of pass mitochondrial bias, which is, I think, number 10. Yes. And then finally, GFA stats. So I'm not going to be actually able to run GFA stats yet, because this tabular file that we have, GFA stats is, so it would be genome assembly manipulation, and we would specify target, and we're going to provide exclude specific intervals. It says intervals because you have the possibility to provide a bed file. So a bed file is going to be the name of the sequence, the start of the sequence and the end of the sequence, because you can remove part of a scaffold and not the whole scaffold. But in that case, if you provide just a list of name of sequences, it's going to remove the full sequences. But it still needs to be a bed file, because it's accepting. If you have a doubt and you don't have your data set showing, you can click on accept format and you see, okay, I need my file to be a bed file. So I need for it to be done running for me to change the type, and then I'll be able to run GFA stats on it. So if you want to change the type of a data set, you click on the little pencil here, you go to data type, and you change to new type. This is different to convert. Convert is going to go from tabular to FASTA or vice versa. New type, you need to do that. You can only do that when one type is a subtype of another. For example, you have FASTQ Sanger, which is a type of FASTQ. You have a bed file, which is a type of tabular. You're just specifying, okay, which subtype of this type I have. Otherwise, you're gonna encounter error, and it's not a conversion, is what I mean. So in that case, I'm not going to do it because it's faster, but you will look at bed for your tabular and you will click on save for the new type. Yeah, so I can run it right now, and basically what you get from out of your GFA stats is your new assembly with without the contamination and without the mitochondrial sequence. And we run that after the scaffolding step, and we run that before the manual curation steps. Yeah, so if you want more detail, I've put the link of the slides in the Discord. You can have more in-depth introduction to genome assembly. It's a 40 minutes long video, but it's very interesting. Gives you exactly how assembly works, what are the different technology. If you are more curious about not using this workflow, but what tool we're using for the same process, and it goes into more detail also with the purging step and scaffolding, you can go to this link. Decontamination is the one I just showed you, and also mitogenome assembly from the same data that you use for your genome assembly. So you can have, with all this workflow together, you can have assembly reference that is ready for manual curation and cleaned up. Yeah, so if you have any question or if you have question that comes later, you can at me on Discord. And it's been a great project. There's been a lot of people involved and still involved. We're updating the workflow constantly and developing new workflows. So yeah, thank you for having me at BGA.
Yeah, thank you very much. I had a quick question, if that's okay. Why only virus, bacteria, and human for contamination removal? Is it just because it's the easiest to automate?
It's not. I mean, it was a shortcut from my part. I think there's protozoa. There's microorganism. You might want to select a different database if you have a stomach sample and you suspect they might be plants. Yeah. You might want to run several runs of it for a different database. One of the issue is because everyone's left.
They all just disappeared at the same time. I don't know if that was they got kicked for some reason. Odd.
Yeah. So the issue is if you have an organism that is not different from that is in the database, then you might want to filter on